Hello everyone, happy to join you today in celebrating another successful year of SESME leading the industry towards smart manufacturing. ArcelorMittal is proud to be a participant in drafting the DOE proposal that led to the creation of SESME and being a member of SESME from inception. My name is Bernard Chukwulebe. I'm the Manager of Processing and Control Group and Digital Transformation Cluster Leader at ArcelorMittal Global R&D located in East Chicago. Our partners in this project include Missouri University of Science and Technology, Purdue University Northwest, Rensselaer Polytechnic Institute, and of course with significant contribution by ArcelorMittal Burns Harbor Plant, Optech, PA Operations, and Global R&D personnel here in East Chicago. The title of the project is Production of Zero Defect Slabs through the implementation of smart manufacturing technologies in steel continuous casting. And Professor Ron O'Malley, Professor Chen Zhou, and Professor Wen Beckett were respectively the PIs for the 3 sub-award tasks under this project. So I'm only giving a high-level summary of the work that has been done by a whole number of people with the highly appreciated funding, guidance, and supervision of SESME. The images on the right show a quick summary of the steel manufacturing process with continuous casting shown here in the middle. Liquid steel is delivered to the continuous caster in a ladle after refining. The ladle is opened and steel flows through nozzles into a water-cooled copper mold, where a solid shell is formed that becomes a container for the liquid steel, which is then withdrawn down the strand by a set of segments and rolls as the steel is water-cooled and progressively solidifies. The fully solidified slab is cut off and sent further downstream for further processing into products for various end-use applications, some of which are shown here. The quality and productivity performance of the slab caster depends largely on our ability to maintain tight control of key parameters of the casting process, both in relation to the steel being cast and the equipment condition. Several sensors as well as physics-based models are already in use at the caster to monitor and control the process and are generating a significant amount of data that can be used to develop predictive maintenance and real-time quality prediction tools to reduce our unplanned turnarounds and product defects. So the goal of the project was to bring to bear the power of smart manufacturing methodologies and technologies to address the top 2 KPIs of the continuous casting process, which are process yield and uptime. On this slide, we have presented in a nutshell the biggest accomplishments of this project. Missouri's Science and Technology successfully demonstrated 2 novel fiber optic sensors. One is the fiber optic strain gauge for liquid core detection and cast operating condition diagnostics. It was able to measure temperature and strain, which then can tell us the location of the final solidification point. And we can use that to validate our slab cooling models to ensure we can run at a high speed when necessary without causing operational problems. And the second sensor is the triaxial optical interferometer for 3D displacement measurement of load on segments, based on which we can determine changes in machine taper and guard against bad internal slab qualities. In the case of Purdue University Northwest, They successfully developed a mock-up version of the digital twin of a continuous caster, and they have added to it a lot of parameters, which is quite a very good tool for demonstrating how the continuous caster works. We did not fully complete all our goals there, but that mock-up is already a very big accomplishment and highly innovative. RPI was able to develop excellent clogging prediction machine learning tool that gave over 80% success rate in correctly predicting clogged conditions in the caster. This is a good example of how powerful machine learning can be, especially when the data scientist is supported by domain experts. The tool can be used to create structured smart manufacturing profiles for continuous casting and made available to other steel companies. So these are the biggest accomplishments of the project. Regarding the impact on manufacturer, with the sale of ArcelorMittal USA to Cleveland-Cliffs, we were not able to fully evaluate what the impact has been on the plant, and there are a number of things that still need to be completed. But our initial estimation of 4.2% savings in yield from the reduction of defects is an equivalent of an annual saving of about $90 million for the whole U.S. steel industry, plus 2.68 pentajoule of energy savings per year, resulting from increased productivity. And we also expect that the predictive maintenance tool alone could save us at least $2 million per caster strand per year, and with many casters in the U.S., that results to quite a bit of savings. With respect to benefits to SESMI ecosystem, we think the advanced sensing solution for strain and displacement in harsh condition, which was developed by Missouri Science and Technology, is available, and under license it can be useful to members of SESMI. The information model for continuous caster also can be transformed into smart manufacturing profiles for use through smart manufacturing marketplace. The digital twin of the continuous caster developed by Purdue University Northwest can be used under license, and the machine learning based clogging prediction tool, which was developed by Rensselaer Polytechnic, can be made available from the smart manufacturing marketplace to other steel companies as well. So with this, I thank you for listening, and this is the end of my presentation.